Hello everyone. In this and the next few videos, we will cover continuous insurances. For continuous insurance, the death benefit is paid at the moment of death. In this video, we will first cover the term and the whole life insurance. Let's start with the end-year term continuous insurance with a death benefit of 1 issued on an individual at age X. The insurer pays a death benefit of 1 at the moment of death if the individual dies within the end-year period, or else if the individual survives beyond the end-year period, the insurer pays nothing. Let Z be the present value random variable for this insurance. With the diagram, if the individual dies at age X plus T, where T is between 0 and N, a death benefit of 1 is paid at this time point at the moment of death. The corresponding present value is the death benefit of 1 times the present value factor, which is e to the power minus delta t. And if the individual survives beyond the end-year periods corresponds to the event Tx greater than N, the insurer pays nothing. We can write out the PMF of Z. Z is a continuous random variable. And therefore, to get the expected value of Z, we use integration. For an end-year term insurance, we start from T equals 0 to T equals N. The present value, which is the death benefit amount 1 times the present value factor, in this case, which is e to the power minus delta t, and then times f tx, the PMF of tx, which is tpx times mu x plus t. The corresponding actuarial notation for the end-year term continuous insurance with a bar with the big A notation. The bar corresponds to the death benefit paid at the moment of death. And then the remaining notation is the same as for the discrete insurance. The second moment, which is the square of the present value times ftx. This is equivalent to evaluate the expected value of Z here with the double force of interest change from delta to 2 delta. Therefore, the corresponding actuarial notation for this, we simply put a pre-superscript 2 with the big A bar notation. And then for the variance, the usual definition, expected value of Z squared minus the square of the expected value of Z. If the death benefit is varying, B sub T, payable at time T, and Z, the present value random variable, is expressed by this. Bt times e to the power minus delta t for t less than or equals n. The expected value, the death benefit amount, times the present value factor, and then times the PMF of Tx. The corresponding expected value of Z squared. And then from that, we get the variance. Let's move on to the whole life insurance. Very similar setting as with the end-year continuous insurance, but the death benefit of 1 is paid at the moment of death whenever the individual dies. The corresponding PMF of Z is simply e to the power minus delta tx, where tx is greater than 0. The expected value of Z, we have this expression where the upper limit is infinity. And if there is a limiting h omega, then the upper limit is replaced with omega minus x. The actuarial notation for the whole life continuous insurance, as you can guess, this is AX, and then with a bar above the A. The second moment, we have this expression. The actuarial notation, P superscript 2, A by X. For varying death benefit, a death benefit of BT payable at time T, we have the corresponding expression. All right, let's take a look at an example. For a 40-year term insurance of one issued on an individual at age 30, given that the death benefit is payable at the moment of death, the force of mortality, mu 30 plus T, is a constant 0.01, and force of interest delta is 0.05. Z is the present value random variable for this insurance, and we are asked to calculate the variance of Z. All right, we can write out the PMF of Z. If T30 is less than or equals 40, the present value of the death benefit is E to the power minus delta T30. If T30 is greater than 40, then the insurer pays nothing, Z equals 0. The notation for this insurance, we have A bar, and then 30 colon angle 40 with the 1 above 30. The expression, 40-year term insurance, so T start from 0 to 40, and then the integrand, the death benefit amount 1 times the present value factor E to the power minus delta T, and then the PMF of T30, which is TP30 times mu 30 plus T. We need to get TP30. By definition, this is equal to E to the power negative of the integral of the force of mortality. And because the force of mortality is a constant 0.01, we can directly get TP30 is E to the power minus 0.01 times T. And we get this expression after substitution. Delta equals 0.05. TP30, we get this expression. And then mu is 0.01. Upon calculation, we get this A bar, the expected value. Next, we do the second moment. The integral from T equals 0 to T equals 40, and then the square of the present value of the death benefit, 1 square times E to the power minus 2 delta T. And we have the same expression for TP30. Upon calculation, we get the value for the second moment. From this, we can get the variance of Z. And the answer is 0.0668. All right, let's take a look at another example. For a special whole life insurance issued on an individual at age 50, the death benefit is E to the power 0.05T payable at the moment of death. Mortality follows the Morpheus law, omega equals 120. Force of interest, delta 0.06. We want to get the variance of this insurance. All right, the solution, the expected value of z, we have this expression. All right, we have omega equals 120, x is 50. We get the expression for bt, and we get the value of delta 0.06. We need to get tpx and mu x plus t. Mortality follows the Morpheus law. Therefore, tpx equals to this expression, and mu is this expression. Do the substitution. Omega minus x 120 minus 50, we get 70. bt e to the power 0.05t times e to the power minus 0.06t, and then tpx mu x plus t is simply 1/70. This is under the De Morphius law. Upon calculation, we get the expectation, the expected value of z. And then the second moment, the expected value of z squared, the integral, and then the square of the present value of the death benefit, and then times ftx. Substitute the numbers, perform the integration, and then we get the expected value of z squared. From this, we can get the variance, which is 0.0209. That's it for today's video. Thank you for watching, and see you in the next video.